Hello, everyone. We will begin. Welcome to Mathspace Academy. So I imagine everybody's at home right now, practicing good social distancing ahead of the long weekend. So we created these classes. It's the first time we do this at Mathspace. And the idea is we know that a lot of you have been affected by school closures. I know schools are trying their best and teachers are trying their best to kind of try and continue things as normal. But we thought for some of you, you might be missing out on some of that extra revision, having and with being in school. So hopefully we thought we could add some value and run through some Mathspace lessons and provide that revision, something to kind of keep you in touch. So starting this week, we'll be running them right through to the end of term 2. We'll see what happens after that. If we're all back to school, hopefully everything clears up and we're back at school. And but if they're going really well and everyone's enjoying them, then we're happy to continue longer than that as well. Okay, so I hope you find it useful. Today, we're going to be doing algebra revision. So on the website for the Academy, we posted our scope and sequence, what we're going through every week. You can come in and out. You can come to all of them. You can come to the ones that you feel are going to be relevant to you. You're going to learn something new. All right, so who am I and why am I qualified to be teaching you here today? So I'm the founder and CEO of Mathspace. I've always been a maths geek. I've loved maths. In high school, I did my HSC maths in grade 11. So I skipped the just for maths and I did the extension 2 and I did really well. And then I went on to university to study actuarial studies, which is just a hard mathematics statistics kind of degree. And the reason I did it was because it was hard mathematics statistics. Came time to get a job and I saw a job ad that said, you got to pass an 80 question maths test inside 8 minutes as like a stage 1. And so I was like, hey, this sounds like my kind of work. So I did that and I ended up getting this job as a derivative trader. So a derivative trader is basically trading options on the stock market. And it was a really fun job. I did really well at it. It's got a lot of, you get to apply, you get to kind of play games and see how, make models of how you think prices are going to change in the stock market. And so I did really well. I was there for 4 years. I actually became a partner. I was the youngest partner at the firm at the time, but I had a little bit of a dilemma. What happened with me is, derivative trading is what mathematicians call a zero-sum game. So I don't know if you've ever heard that term. What a zero-sum game means is that somebody can win only if somebody else loses, right? And so it was actually at the global financial crisis at the time, where the economy was kind of going crazy. That volatility in the market was really, really good for a derivative trader. But for the rest of the world, it wasn't going that well. And it made it really clear to me that I want to do something where I'm actually adding value, not being the better player in a zero-sum game, right? So that's how my mathematical brain thought about it. So I quit and I wanted to become a maths teacher. A friend of mine, my co-founder at the time, he said, what are you going to do now? You were this hotshot derivative trader. What are you going to do? And I said, I want to be a maths teacher. I want to actually add value. And he had this idea of helping more students using technology. And so that's what kind of Mathspace has the idea behind it. And as soon as he pitched it to me, I was like, yes, that sounds fantastic. So instead of, teaching a class of students or 5 classes of students, is there a way to build something where we could help every student work through a maths problem as they're going through? That was the general idea, and that's what Mathspace has become. So that's just a background of who I am. Okay, now, before we go too far, I want some quick housekeeping. This class is going to cover the Year 10 curriculum, not the 10A curriculum. So we're not going to get into the advanced curriculum at this stage. If there's demand for it, email us, let us know, and we'll go through some of the harder stuff as well in the 10A curriculum. But we're going to take the baseline of just all of the Year 10. We can't cover everything in an hour a week. So this is not going to be a deep, everything you need to know about it. What I'm going to try and do more is give you that conceptual understanding. We're kind of trying to tie it all together. We will follow the Mathspace curriculum. Hopefully all of you are familiar with the Mathspace curriculum. If you don't have access to a login, ask your teacher and you'll be able to practice the questions on Mathspace, some of the topics that we talk about. The class will be recorded and available at mathspace.co/academy. So you'll be able to review it there later if you want to go over something in more detail. I will use polls to get a sense of your understanding. I haven't launched one of these polls yet, so I hope they're all set up correctly. If they don't work, we're going to use the chat instead, but let's see. We're going to try with the polls first. You can use the chat, but please use it sensibly. I'm not going to turn it off. I'll be looking at it every now and then, but I won't monitor it much. So make sure you use it sensibly. We're all here to learn. So anything where you want to talk to each other about the learning, you have some questions about what's going on, feel free to. But for formal questions, you should see a Q&A button. So if you want me to actually answer the question, then use that Q&A button, and I'll actually pause a couple of times throughout and take questions from you and answer them live. All right. All right, now a bit of an exercise to get our minds going. We're going to use the chat to answer this one. All right, we're going to be talking a bit about this concept later, but I just wanted to warm you up. So we have a pond that starts with one lily pad. Each day, so we got this one lily pad here in the corner. Each day it doubles in size. So day 2, you got 2 of them. Then the next day you got 4 of them. After 30 days, the whole lily pad fills the pond. How long did it take for the pond to be half full? All right. So if you just click on the chat button, I want to see answers coming through on the chat. Have a think about it. And when you're answering, if you can click to all panelists and attendees so that everyone sees your answer. All right, I'm going to give you a minute to have a think about it. Who's going to be the brave person that puts it out there first? 29. All right. Everyone agree with 29? Got a not sure? We got a 15. 29, maybe 28. All right, cool. So it's good that you took your time to kind of think about it. We got 29 as it doubles on the last day to fill the pond. Nice one. All right, cool. Am I sharing my screen? I'll make sure yep, I'm sharing my screen. So you should be able to see the question on my screen. For anyone that's joining, I'll make sure that's the case. Yeah. Yeah, the screen should be being shared. Okay. All right. So yes, the answer is actually 29. So if you thought about this really quickly, the first thing you might say is 15, right? It takes 30 days to fill the pond. But this is something that we call exponential growth. And this is something that you should probably have heard a lot about in the news lately with what's going on with COVID-19. That's how we're going to talk a little bit more about that. And if we have time at the end, I'm actually going to do some simulations of COVID-19. Pretty cool simulations to give you an idea of how quickly it spreads and how effective social distancing can be. So 29 is the correct answer. It's not 15 because on that last day it doubles again. So the previous day it was half full. All right, now that we got our minds ticking over, let's get started. So today we're going to be talking about algebra. We're going to be doing this over 2 lessons, revising all of algebra. So algebra is the part of mathematics where letters and general symbols are used to represent numbers and quantities, right? So this is the first time where you start going, wait a minute, you can have the letter X to mean a number. That's what algebra is about, right? So what do you need to know in year 10? These are the parts of algebra you need to know in year 10. So I'm sure everybody would have had some understanding of algebra before today. So I'm not going to definitely go through all the basics. But in year 10, you should be looking at the adding and subtracting algebraic fractions, as well as multiplying and dividing, negative indices and formulas. And we're going to go through that this week. Okay. Next week, we're going to go through the factorizing and expanding and the rest of it. Now, I'm going to try and launch a poll here just to get a sense of, let's see, launch polling. Hopefully you'll see this poll. I want to get a sense of how quickly you want me to go today. So how do you feel about algebra? And we've got 3 options there. It's so hard, it's okay, but I could use a refresher, or I'm all over it, okay? I'm gonna use this to just help me, guide me how fast I should be going today. Okay, I'm going to give you 5 more seconds to answer that. Okay, I'm going to share these polls with you. Hopefully you're all seeing that on your screen now. So I see that 67% of you said it's okay, but I could use a refresher, and 33% said I'm all over it, right? So that's good, because I'm not going to be able to go through it from start to finish for people who find it so hard. I'm really going to go with the refresher approach, okay? So that's good. That gives me a good sense of how quickly I should go today. All right. Okay, don't worry if you're not seeing the poll. I've got the information I need. For anybody who does need extra help and wants to actually go through and learn all of algebra from scratch, or wants to really revise it in detail, we've mapped all of Eddie Wu's videos to the Mathspace curriculum. So if I go through something today on adding and subtracting algebraic fractions, and you need some extra help from there, you can look at Eddie Wu with a more detailed explanation of all of that, okay? So that's something to help you out if you're looking for detailed lessons. Today, we're going to go through the quicker version. Okay, we've already been through that. All right, so let's begin. We cannot talk about algebra without talking about the father of algebra, the founder, Al-Khwarizmi. His anglicized name is Al-Khwarizmi. So he's actually from Persian origin, and he lived most of his life in Baghdad. And this man was a freak. So he had mastery of many subjects, including obviously mathematics, but also astronomy, Islamic sciences, music, history, and geography. And when I was like just doing some research preparing this, it dawned on me a little bit that, you know, he lived in Baghdad. Baghdad at that time was the center of scholarship so they had this place called the House of Wisdom, where all the scholars of the time would come together and translate all the old works of the ancient Greeks and of Greek philosophers and build upon them and build upon their mathematics. And so you could see them kind of, you know, sitting there, that's a statue of him there, stroking his beard, just thinking about the world and mathematics and astronomy and how the world comes together. And Baghdad used to be a real center of learning. You know, obviously today things are different. You know, I think it would hurt Al-Khwarizmi to know that, you know, some of the algebra that he helped create was also kind of led to everything we do today, good and bad, the computers, but also the kind of the guided missiles that, you know, have caused some destruction in his homeland. So I just thought let's give honor and tribute to the great Al-Khwarizmi, who without him, I've got a quote from one of the CEOs of HP, Hewlett-Packard, one of the biggest computer companies in the world, who said, if Khwarizmi was not born, then the science of computers would not have developed as we see in our life. The programming language is based on trigonometry and derivatives, which was developed by Al-Khwarizmi. Okay, now the word algebra comes from actually his book, Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, which means the book of calculation by restoration and balancing. Basically, he wrote the book on balancing equations, the first person to do that. Al-Jabr, which means the restoration and balancing, that's where the word algebra comes from. Okay, my surname is Jabara, so I kind of like, I'm not related at all, but it would be so cool if I was. All right, so the letter X, where does that come from? It actually comes from the word shay in Arabic, which means thing. X just means the unknown thing, and we use it all the time, not just in maths now. We use it for like the X-Men, X-Files, X marks the spot for the treasure. And whether it all started from the word shay in Arabic, which in Spanish, so I watched a TED talk on this, and we don't know for sure, but this historian tracked the history of it, and he believes that it came from that word, which became chi in the Spanish translated it, which is the Greek letter that looks like an X, and then we kind of made it an X from there. So, all right, I'm going to move into the common misconception. Now, like I said, today I'm going to go quite quickly and really try and give you a address the core of what algebra is. So hopefully I want to give you an angle that maybe your teachers haven't given you in class, a different way of thinking about algebra. Now, there's a common misconception. A lot of people kind of, when they talk about algebra, they say, oh, it's like X is bananas and Y is apples. And so you can't add apples and bananas. That's actually not the best way to think about it. The best way to think about it is X is an unknown number. So a better way, if you wanted that kind of analogy to kind of give you something in your mind, is to think about it as X is the number of bananas in a box, right? How many? It's an unknown number. And Y is the unknown apples in a basket. And so when you think about, okay, why can't we add X and Y together? It's because if you don't know how many bananas there are, the bananas in a box and the apples in a basket, if you don't know how many there are in each, you can't add them together. But you can add X and X. If you had two, X is the number of bananas in a box, and you had another one, that's the same as having 2 times the number of bananas in one box. So that's 2X. So that's a good way of thinking about it. It's not complete because X can be a negative number. So, when you think about it this way, it has to be positive, the number of bananas in a box, but it's a better way to kind of help you grasp it. So the whole key to algebra is this then. Since the variable X just means an unknown number, then anything we can do to numbers, we can do to the variable X. If you understand this concept, then you are well on your way to mastering algebra. And I want to give you an example of this now. I'm going to launch a poll to illustrate this. Okay, it's a true or false question. If I want to solve X plus 1 over X plus 4, okay, first thing I do, cancel out the X's, and then that just gives me a quarter. Let me launch a poll and just check with everybody. How do I go to my next question? Here we go. True or false, launch polling. Okay, is that true or false? Okay. All right, I've got some results coming in. We've got some mixed results. Some people saying true, some people saying false. I'm going to give you a chance to change your answer by showing you an example. Okay, so remember X just means the unknown number. So let's say the unknown number was 2. Then what we're saying is 2 plus 1 on 4. Let's cancel out the 2's, and that gives us a quarter. Okay. Now, having a look at that, do you want to change your answer? True or false? Okay, somebody's not seeing the poll, everyone else is. So if you can't see the poll, you can let us know on the chat what you think. But we are getting responses, so I'm sure it's probably on your end if you cannot see the poll. All right, I'm going to end polling and share the results. Okay, so correctly, most of you identified that this is false, okay? And remember what we said on the previous slide, that basically what applies to letters applies to numbers. So this case over here, the 2 plus 1 over 2 plus 4, that's actually 2 plus 1 is 3, 2 plus 4 is 6, so you get 3 on 6. And so 3 on 6, we all know is a half, not a quarter. So if it doesn't work for X equals 2, then it doesn't work. It has to work for all possible numbers for X, right? So this is a really important concept and really the groundwork of algebra. If you can do it, whatever you can do with numbers, you can do with the letters. A really common error that I see all the time, probably the most common error, is this error here, where you have people canceling things in the numerator and denominator when they're not multiplied by each other. You can see here, it does not work, right? 2 plus 1, 2 plus 4, you get 3 on 6. You can only cancel common factors when they're multiplied by each other. You understand that, it'll really take you a long way towards mastering algebra. So we're going to look at a few questions now, and I want you to keep that in mind. You can only cancel things when they're multiplied by each other. All right, so a couple of quick examples, and then we'll move on to indices. So All right. I'm launching a question on Mathspace. Okay. 2x on 3 plus 2x plus 5 all over 6. We need to simplify that. Okay. What is the first thing we need to do? Feel free to answer in the chat. So remember, we're going to think about these as numbers. So forget about the two x's and the x's in there. If we have something over 3 plus something over 6, first thing, common denominators, perfect, right? And the common denominator in this case, 3 and 6, nice easy one, is just 6. So we go with the common denominator of 6. Now to get to that, to get from 3 to 6, we have to multiply by 2. So we're going to multiply 2x by 2, and that's the 4x. And then we're adding 2x plus 5 on 6. I'll just copy and paste that straight in. Right, so we haven't done anything with the algebra yet, right? We're just dealing with these things like they're numbers. Something over 6 plus something over 6. Next step, because we have a common denominator, we can just add the numerators. So we got 4x plus 2x plus 5. Now, I'm going to put this thing in brackets. Now, in this case, I don't need to put it in brackets, but it's really good practice to do this. And you'll see why in the next question when we start doing subtraction. This is really important. Whenever you have a algebraic fraction, that it's the whole numerator that's over 6. So when you start combining things, putting the brackets around makes you remember that it's the whole numerator that we're talking about there. Okay, so again, in this case, it doesn't make a difference. We have 4x plus 2x is 6x, and then we have the plus 5. Okay, too easy. So that's adding algebraic fractions. Now let's look at one with subtracting algebraic fractions. I'm going through these quite quickly because I know that you said that you just need a bit of a refresher. Okay, so again, same thing. First step, common denominator. We happen to have, I'm going to give one so that I'll generate new numbers just so we're not always doing the same ones. All right, let's look at this one, 5 and 25. So common denominator in this case is, again, 25 is just a multiple, so we can just go with 25. Now, I know one way that people do this is to cross multiply, and you end up with, so you could end up with 5 times 25, 125 as a denominator. It will work, but it will require dealing with higher numbers and simplifying later. It saves you so much time if you can actually find the lowest common denominator and not just any common denominator. Okay, so to get from 5 to 25, we had to multiply by 5. So now we need to multiply the numerator by 5. Okay, this is now a common mistake. I see this so many times. Yeah, 30x plus 7, right? We're multiplying that by 5. Correct or incorrect? Definitely incorrect, right? This is why I really recommend going with the brackets. What we're saying is we're multiplying the top by 5. That means the whole top, 6x plus 7 by 5, right? So really important to know that it's the whole numerator that we need to multiply by 5. And then we're subtracting x minus 4 over 25. I'll just copy and paste this in. Okay, now that we have our common denominators of 25, we can just subtract the numerators. So I'll keep this in this form for now. And we're going to subtract. All right, remember what I said about brackets? We're subtracting the entire numerator. So let's put brackets around it, x minus 4. And you can see, again, this is a really, really common mistake that people don't put that brackets and they're like, oh, we're subtracting x minus 4. And you'll end up getting the wrong answer if you do that. You're subtracting the entire x minus 4. Right. Now the next step is to expand these brackets. So you might remember how to expand the brackets. Let me try and annotate to you. Okay, I'm going to annotate on the screen. We're looking to do 5 outside of 6x plus 7. Now, you've probably seen this before. You just multiply that by that, and then multiply that by that. Now, when you think about why that is, and you actually do this a lot when you're doing mental mathematics. So again, anything that you can do with numbers, you can do with letters, right? So I want to give you an example of when you might do this with numbers. Let's look at an example of something like 6 times 15. Okay, if I told you to work this out in your head, 6 times 15, I know the way I would work it out in my head, and I think a lot of you probably work it out this way, is you'd go, okay, 6 times 15, I can't really do that in my head, but I know that 6 times 10 is 60. And then I've timed by 10, so now I can go 6 times 5 is 30. And so I can go, okay, so that's 60 plus 30, which is 90. Okay, sorry for the extra lines on the screen. So what you've actually done there, and so that's a really good way to do it, but what you've actually done is you've been using this rule. You just went, it's 6 times 10 plus 5. So you've actually, let me use a different color to show. What you've done is expand the brackets. You've gone 6 times 10 plus 6 times 5 is what gives me 60 plus 30. So that's what expanding is all about. It works with numbers, it works with letters. You're doing the exact same thing. All right. Now that we know that, I'll turn off the annotation. So we need to do the 5 times the 6x, which gives us 30x. And then the 5 times the 7, which gives us 35. And we're doing the same thing over here. Now, when you have a negative outside the brackets, why it's important to have the brackets, it's like having a -1. So -1 times x is going to give us -x. And then -1 times -4 is going to give us a positive. Okay. So final step, collect like terms. 30 bananas in a box minus 1 box of bananas. I'm going to get the same as 29 boxes of bananas, right? We can do that because we're talking about the same thing. And then 35 plus 4, we can add them together to get 39. And that is subtracting algebraic fractions. All right, 2 more examples, and then we'll get on to some of the more interesting stuff today. All right, we'll look at a multiplication example. Okay, multiplication, again, just what you can do with numbers, you can do with letters. So if you had multiplying fractions, the way to multiply them is to just multiply numerator by numerator and denominator by denominator. So this one's nice and easy. We just go times the numbers together to get 45. And then the letters ST, we can times them together. And then we can divide by 2 times 8, 16. And then we have also ST. Okay, but we're not completely simplified. We need to cancel out common factors. Now, these are all multiplied by each other. Remember, you can only cancel out things if there's multiplication in between them. So it's 45 times S times T, 16 times S times T. The times S times T can go away. And we get 45 on 16, which is fully simplified. Okay, we'll look at a harder one with dividing algebraic fractions. Okay, so we have 2 u cubed. We're going to talk about indices in a second, but hopefully you all know that u cubed just means u times u times u. And we're dividing by this other fraction over here. So in this case, what do we know about dividing fractions? I'd love to kind of explain to you why this is, but it'll take a while to do it. So I'm just going to at this stage, I'm just going to say, you know, the rule that dividing a fraction is the same as multiplying and flipping. So what we need to do here is 2u cubed over 4v. So the first fraction stays as it is, but the second fraction, we need to change the division to a multiplication and then flip the fraction. Okay, so basically, fraction is division. So and multiplication is the opposite. So if you want to change the division to a multiplication, you have to flip the fraction over that second one. I might send you something after this to kind of try and explain that in a bit more detail. All right, so that's the first step. And then from there, by the way, if you're ever stuck on Mathspace and you don't know what to do next, just jump in there and ask for a hint. So best thing to do next is to cancel out common factors between the numerators and denominators. Now, this is always helpful. This is a really good way to be more efficient when answering these questions. We could multiply these first and then divide and then cancel out at the end, but it's always easier to deal with smaller numbers. So if you have the opportunity to cancel out common factors first, then go ahead and do that. So let's see, what are the common factors we can cancel out here? We have u's up the top and v's down the bottom, so we can't really cancel out anything there. We have a 4 here and a 4 there. Can we cancel out a 4 from this side with a 4 on the other side? The answer is yes, as long as there's a multiplication in between. So I think to demonstrate this, probably the best way to demonstrate that why you can do that is to say, okay, the next step we're going to do is times by 4u, and then we times the bottom by 9v, and we can get rid of that. And so now at this stage, because everything is multiplied, it's 2 times u cubed times 4 times u, and then divided by 4 times v times 9 times v, because everything is multiplied, we can cancel out common factors. And the easiest way to do that is there's a 4 there and there's a 4 there, so we can just get rid of those. And I think that's all the common factors there are left. And now we simplify that. So what's u cubed times u? So remember, u cubed is u times u times u. And now we added a 4th u, so we're going to get u to the 4. And I'm going to talk about this in a second in a bit more detail. But hopefully you just know that that's the way it works. And then v times v is going to be just v squared, just a simpler way to write it. And so that's how you divide algebraic fractions. All right. Cool. So I'm going to pause and just see if anyone has any questions. So if you have any questions along the way, there's that Q&A button, and you can just press that Q&A button, and I'll have a couple of points throughout today where I'll pause and actually just take your questions. All right. At this stage, I don't see any questions, so I'm just going to move on, and we're going to start talking about negative indices. All right. We kind of touched a little bit on indices there. We'll do a bit of a deeper dive into negative indices. But before we do, I just want to discuss indices in general. Like I said at the start, exponentials has been something that's been in the news lately, what exponential growth means. So I want you to think about exponential growth with this question. And I will launch this poll. So imagine that you're now sitting at home and you get a job offer. The job offer is to, I don't know, make online maths videos, okay? And it's for 20 days. You got a 20-day contract, and you have 2 options, okay? So your boss comes along and says, look, I'm gonna give you 2 options for how you get paid. I can pay you $1,000 a day, really good rate, or I can start you with $1 a day, and every day I'm gonna double it. Which one would you prefer? I've launched the poll. All right, have a little bit of a think about it. I'm going to give you a minute, another minute. No poll? I'm going to launch this poll again. Sounds like there's no poll. Okay, I've relaunched the poll. Hopefully you can see it on your screen now. Okay, would you rather go with start $1 a day and double every day, or would you take $1,000 a day? All right, interesting seeing these results come in. All right, for those who have answered that question, in the chat, how would your decision change if we said only for 10 days? Okay, so it's a 10-day contract. You can take $1,000 a day, or you can start with $1 and double daily. It's only a 10-day contract. Would your decision change? All right. Yeah, some people saying yes, their decision will change. Yep. All right, cool. So time is a real factor there, how long it goes for. All right. I'm going to end polling and share results. And I'm going to say I'm pleasantly surprised at how everybody is understanding. So we got 94% who went for the $1 a day option, which is the correct approach. We're going to actually now simulate and see why that works. So let's take a look together. All right. Hopefully everyone can see my screen here. I've got a spreadsheet. I've got day on the first column, and it's just gone 1, 2, 3, 4, 5, 6, up to 20. And then my column B is $1,000 a day. And then over here, I have, let me just get rid of this one. Okay, and over here I got $1 and we're going to double daily. Okay, and then we're going to graph these answers. So if we're going to double daily, what we need to do here is we're going to say this is equal to the cell above it, and then we're going to times, which is the star, times 2. Okay, and then on the spreadsheet, what we can do is we say that's the cell above it times 2, and then we want to copy that across to this cell. So it's going to be the cell above it times 2. And we're going to copy that across again to this cell above it times 2, cell above it times 2. So after 5 days, the blue line here is how much you're making if you're starting with $1 and doubling daily. Day 5, you're making $16. You're going to need a long way to go to catch up to 1,000, right? Actually, not going to need that long. Watch what happens pretty quickly. This is what exponential growth looks like as you go through. All right, by day 10, you're making $512 a day. On day 11, you're making more money per day than the $1,000 a day. And that's the nature of exponentials. It kind of starts off slow and then it can just really, really ramp up. So it's really hard for the human to kind of understand exponential growth. And I think at the time now with COVID-19 around, we're starting to understand just how quickly things can spread. If one person is infected and on average will pass it on to 2 other people, then what seems like a really small thing with only 10 people infected, 16 people on day 5, in just the space of another 5 or 6 days, you can start talking about 1,000 people. And if we don't do something to stop this, then this is what it can look like on day 20. Now, in dollar terms, this is fantastic. If anyone offers you exponential growth of your wages and you take it for sure. Look, the 1,000 is almost invisible now, like so small in comparison to the $524,000 that you're going to make on day 20. So that's kind of the turning point. Now, let's have a look at what happens if it triples daily, okay? And so I want you to think about this with the coronavirus as an example. So we're going to start with 1, and then we're going to multiply the cell above it by 3, okay? And then that's going to become 9, okay, 27. It's almost invisible, right? You can't even tell the difference between it's growing at, on average, one person infecting 2 people or infecting 3 people. But pretty quickly, okay, we're starting to see how quickly that, we're seeing something there, right? We're at 6,000 over here. And at about the day 13, we're about the same mark, right? So we got there 7 days earlier. And then if this was to keep going for the 20 days, look how big that gets. The blue line is now invisible. It doesn't even compare because of how many millions of people are affected with it going at this rate. Now, if we have time at the end, I'm going to actually go through some really cool COVID-19 simulations with you, try and understand a bit of the maths that goes on here. This is really simplified because, of course, there's so many things that happen. So people actually recover after. They don't infect as much people. Obviously, people get quarantined. That reduces it down. So I'm going to look at a couple of simulations with you a bit later. But I just wanted to give you an idea of just the mind-blowing exponential growth, what that actually means. Right. Okay. So I'm impressed that everybody kind of got a good understanding of that. And I think I can credit the situation right now with that. Now, in year 10, you start getting exposed to negative indices. So negative indices, you would probably have learned it as this formula. A to the negative x is equal to 1 over a to the x. Now, I want you to understand why. Why is it that a to the negative x equals 1 over a to the x? And the best way to show this, I think, is to just try and follow the pattern that's going on here. So I'm going to start with 2 squared. Now, if I want to work out 2 cubed, what I need to do is multiply by another 2, because we have 2 squared is 2 times 2, and then I need to times by another 2 to get 2 cubed. So watch what happens to this pattern. As I go 2 cubed, I double it. As I go to 2 to the 4, I double it. As I go, so every time I increase the exponent by 1, I'm doubling, I'm multiplying by 2. Now I want you to think about what happens when you go backwards. Every time I subtract the exponent by 1, I'm halving it, okay? So I'm dividing by 2. So I'm going to go backwards. I'm going to divide by 2 to get 8. 2 squared, divide by 2 to get 4. 2 to the power of 1, divide by 2 to get 2. Now, what do you think is going to happen when we have 2 to the power of 0? We're just following the same pattern. So we need to divide by 2. So 2 to the power of 0 is 1. Now, this is one of those things where you kind of like, you learn it just as a rule. Anything to the power of 0 is 1. But now you've got a bit of an understanding of why that is. That you're actually starting with 2 to the 1, and then you're dividing by 2. And if we keep going, the same thing should happen, right? Maths follows this beautiful logical pattern. It's the beauty of mathematics. It explains the real world. So if we expect this pattern to continue, so if I say 2 to the power of negative 1, it's 1 divided by 2, which is a half. And if I divide that by 2, 2 to the negative 2 is 1 over 4. So you can see what's happening here, that the answer as I keep dividing by 2 is just 1 over 2 cubed. And that's where this formula comes from. And we look at it that way. Okay. I did have an example I wanted to show of the negative indices in action. It's not in my slides, so I'll just bring it up. Okay. So actually, while it's coming up, I want to show you something about negative indices over here. Let's imagine that after 10 days here, I'm going to get rid of this, that we started to apply social distancing measures. And so we, instead of one person on average affecting 3 people, because we got onto quarantining those people, we got one person on average affecting only 0.8 of a person. So we get a previous cell and then 0.8. So how do we on average only affect 0.8 of a person? Some people would affect more. Some people will affect 1 person. Some people will affect 0. And so on average 0.8. So if that was to happen and we would continue that, you can kind of see what we've been calling flattening the curve, right? That if we can get the infection rate that 1 person infects less than 1 person, then we're talking about negative indices happening. And that's what a negative index looks like. The curve starts to flatten. Right. Side note, let's go jump into an example of a negative index. I wanted to look at this question. Okay, so simplify the following, give your answer with a positive index. All right, so a couple of ways we can look at this. Firstly, let's look at the number component. 20 over 5, that's just 4. So we can kind of just quickly go, yep, that's just going to be 4. And now let's look at the exponents. So remember, we now know what negative exponents are. There's a few ways we can do this now. If we don't like to deal with negatives, we can just apply our new knowledge of negative exponents and just change them to positives. How do we change them to positives? If it's in the numerator, we have to take it to the denominator. If it's in the denominator, we have to take it to the numerator. So we basically flip the fraction, means we can flip the sign on that index. So one way to do this is to say, I'm going to put the -6 to the bottom, and that's going to become 6. And I'm going to make the -2 to the top, and that's going to become +2. And now we're dealing with a very regular, no negative indices, right? So we end up with x squared of x to the 6. Dividing top and bottom by x squared, we end up with x to the 4. Okay, but I'm going to go another way. If going back over here, we wanted to apply our rule on, let me annotate on the screen. So if we wanted to apply our rule that x to the m divided by x to the n, hopefully you've learned this by now, is equal to x to the m minus n. So when you're dividing powers, you can just subtract the indices. So if you did it that way, then you could go, it's 4x to the -6. I'm going to put the power in brackets. I won't put it in brackets because I need another bracket. So -6. And then we're going to subtract the one that we're dividing by, -2. So we're subtracting -2. And so you could do it that way. And then -6 minus becomes plus. Right? And hopefully you understand why that is. It's just a change in direction. So if you're going negative and then we change the direction, then you're back into the positive direction. So -6 plus 2 is -4. And then the question says, giving your answer with a positive index. So if I want to get the -4 to the bottom now, then I'll make it +4. So to make it positive, I just need to get the index to the bottom. So there's an example with negative indices. All right, I'm going to look at any questions, and then we're going to do some COVID simulation some pretty cool stuff, which I want to share with you. All right, just looking at the questions, we just have one question. If we skip a step, student skips a step and still get the answer right. Sometimes I don't get green. Sorry if this was addressed already. I joined live. Okay, so just with explaining the Mathspace marking, if anybody wants to know more about that, this means it's a correct step, but it's not something that Mathspace had in their backend. So you kind of went about it in a different way. You'll still be marked right. If you ask for a hint here, we will give you a hint on the step that we had as a step in our solution. So in Mathspace, you can skip straight to the answer. You can do all your work, say on paper, and just skip to the answer. But you know, and if you know the answer, that's fine. But if you don't, then what you can do is put in your steps, and we'll work out. We'll give you feedback on each step as you go along. So hopefully that answers your question. All right. So that's it for what I wanted to get through today. Instead of talking about formulas, let me just kill this annotation, get this off the screen. Okay, if anyone has any other questions on the chat or anything, please ask away. Otherwise, I'm going to go do some fun stuff with COVID simulations. So let's take a look at that. All right, first one I'm going to do is the billboard analogy. And once we get to 11, we'll just wrap up. But I think you'll find this stuff interesting. I spent a lot of time on this last night. It was fun to kind of look at what happens. And I mean, this is just really interesting about how mathematics is, you know, something to think about, I guess, when you're home right now, is just how important mathematics is in understanding the world. So right now, without these mathematical models, without these people thinking about mathematics of coronavirus, we would see cases just really, really bad. So mathematics has, I think everybody has to have a good understanding of mathematics to make sense of, like, why are we being told to do what we're doing? So I can't stress enough just how important mathematics is in learning. And this is a really great example to kind of look at it in a real world case scenario. So here we've got a simulation of a sick person in brown and a healthy person. Every time you touch a sick person touches a healthy person, they get them sick, right? Pretty quickly, everybody gets sick. Now, in actual case, we can have also recovered people, right? So a recovered person is, we're going to have them as purple in this simulation. And that means that they got sick, but then they got better. So here you can see sick person makes another person sick, makes another person sick. And these people are recovering from that. Okay. So this is just to give you a sense of what this simulation is, right? So you now know what all the colors mean. The brown is sick, the purple is recovered, and the blue was the healthy person. All right, now it starts getting interesting. Let's take a look at what happens in a community of 200 people if you just let everyone go at it like crazy. People just walk around randomly, they jump on trains, they jump on a bus, they go to work, they get a thing, and pretty quickly, this is a graph of what's happening over time. Really quickly, exponentially, people are getting sick. This fast, really quickly, everybody's got sick. So now people are recovering, and that's just, they're recovering because they got sick and they're recovering. So that's what that looks like if you just let everybody go for it. Okay, let's see now. So this is a case now where we introduce quarantine. So if you say, if the government says, you know what, we're going to try, once we identify a sick person, we're going to try and kind of like zone them in their own zone. We're going to try our best. It's not always possible to do, but we're going to try our best. So this is a simulation of what that might look like. You're like, oh, there's a sick person. Let's just close down their city. The problem is that it's impossible to close a city down completely. So as soon as it starts opening up a little bit because people start breaking the rules or whatever, then it starts going into the rest of the population. And then before you know it, you know, this is infected. So there's no real reason to just quarantine these people anymore. So you start to open it up, and soon enough, everybody in the whole country is infected, right? So if you compare the graph that's happening here, you had it kind of slowed the rise over here by thing, but you can't really stop it completely. And so that's the effects of quarantining. Now, if we keep going down, this is now social distancing. What happens if some people are just not moving around like they used to? Okay, so in this next one, we assume that a quarter of the people are not moving around, or a quarter of the people are still moving around. Okay, so anyone that's not moving, because they're not moving, this is a really good simulation to give you an idea. Obviously, it's just simulating real life, that if people are not moving around as much, then there's less chance of them getting into contact with infected people. So here we only have 25% of the population is allowed to move, and everyone else is just doing the right thing and staying at home. You can see how much of a difference that makes, that we don't actually get, it takes a long time to get for everyone to get infected. And also not everyone in the end gets infected. This is something that, you know, our hospitals will be able to cope with the number of infections if we have this social distancing. Now, the last one on this is the same thing, but now more people are social distancing. So here we only have 1 in 8 people that's allowed to roam around. Let's just say only essential workers, people who have to for their job. So by doing this, and everyone else is just still staying at home, right? Then the idea, by doing this, you can see you have it really under control. There's some infections going on, but it's not that much, but it requires really strong social distancing. So that's a pretty cool simulation. We've got a couple of minutes left, so I'll just quickly take you through another one. Somebody asked about the recording. Will it be available? Yes, we will have the recording available on mathspace.co/academy. This one's a really cool one. It's a different type of simulation. And this one looks at, make it a little bit bigger. This one gives you some sliders, right? So here we're talking about an infected person is just this person in the middle, and everyone else is susceptible. That means they could get it. They haven't recovered yet. Let's look at what happens. Just to simplify things, every time you sneeze, everybody that's close to you gets it. Sneeze, everybody that's close gets it. Sneeze again, everybody that's close gets it. Everybody that's close gets it. Everybody that's close gets it. And you can see it just growing exponentially. They can get bigger very quickly. In actual case, people can recover. So let's say they recover after 2 days. So the dark gray is somebody who's recovered, had it, but then recovered. Okay. And now this is the part that's scary. So if you don't know you have it, so let's assume that a virus has 7 days where you don't know you have it. So, and that's going to be this light red dot. So you're spreading it without knowing, right? So all these people have it now, but they don't know. And then only after 7 days, you now know that you have it. All these people have it and are walking around in the world without knowing. Only one person knows. The next day, only those people that are infected know, because it takes 7 days for it to happen. And this is one of the scary things about coronavirus, is there's this incubation period where you don't know that you have it. You might be carrying it and passing it on to other people and not showing any symptoms. So that's a pretty scary scenario, because if I just play this out, you know, it just goes really crazy. All right, so we're running out of time. Feel free to leave if you don't have time, but if you're finding this interesting, I'm happy to go through the rest of this, and I'll share the links so that you can go through it in your own time. Now, here we start introducing, this is like algebra in action. It's just, I don't know, so fascinating, amazing. We're introducing now a probability, so that a chance of transmission. So not everybody you come into contact with is going to get it. Let's imagine that only 50% of them get it. So if we step through what happens, it's that all those people around you, but we're adding a probability. So we're just giving it a 50% chance that they get it. That's why it's not necessarily going to everybody around you. Sometimes it will, sometimes it'll go to a few people, sometimes it'll go to a lot. And again, there's that incubation period, right? Now, if I play this fully as it goes through, you can see it spreads everywhere based on this transmission rate. Now, transmission rate, if that transmission rate is high, that every second person you come into contact with, you know, you're going to infect. There's really no stopping this kind of thing. When that gets a little bit lower, then let's reset and see what it looks like. So anything we can do to reduce the transmission rate, and you can see at 0.32, it stopped. It can be handled. So the kinds of things we can do to reduce the transmission rate are things like washing your hands. Right? By washing your hands, you're reducing the chance of people getting it. If that transmission rate gets anywhere like around that level in this model, you can see it doesn't stop. And if it gets really high, then it just goes like crazy. Okay, so that's where washing the hands becomes really important. All right, travel is another one. So how far you travel. So here's an example, let's say with a travel radius of 15. So basically that means up to 15 people away is how far you can infect somebody. Okay, so this is it where you can infect people all up to 15 people away. And if I play this, you'll see how quickly it goes. Really, really fast. And you see what the graph looks like over here. Okay, now if you reset, and I'm going to change the travel radius to down to like, so 15 was over here, that's how far it can go. Let's go down to like 5, that people stay local in just their areas. And let's play that simulation. You can see it grows, but not as fast as before. See how high it went over here and over here. That's why on this long weekend, the government is telling everybody, please don't go travel like you normally would, you know, go on a 4-hour drive. If you do have it, you've just introduced it to a whole new community potentially, right? If you had it without knowing, you know, you haven't just, it's not isolated just in your community where you live. You now have gone off to holidays to the Central Coast, wherever you go, you've gone interstate, you've gone from New South Wales to Queensland, you've just introduced it to more people. So that's how important the travel radius is. It just significantly reduces how far. And the lower that is, so if I reset and just go travel radius of 1, you can see you can only infect just your kind of direct neighbors. Look how much of a difference that makes to the graph of how quickly this red line grows. Okay, it grows a lot smaller, lot slower. All right, I'm going to end it there. There's a few more things you can play with, but I hope you've enjoyed this. I hope you've learned something about algebra. Give us feedback if we went too fast, too slow, if you enjoyed some of my sideshow, not necessarily talking about algebra. Well, it's all related to algebra for sure, but some of the more interesting real life applications. And I hope to see you all next week. I hope you enjoyed that. And advice from me is keep learning on, you know, in this time, use this time wisely. Don't just binge on Netflix, you know, have a balanced life. Make sure you stick to your studies. The fact that you're at home doesn't mean that you can't learn. You know, take some inspiration from Al-Khwarizmi and sit there and think deeply about the world. And this is a real good time to do that. So have a great week and hope to catch you all next week. Have a great Easter long weekend as well. Bye, everyone.